Okay, good. Okay, very good. Okay, so if you're not speaking, please just mute the mic, right? Okay, good. Okay, so any questions about the two homework problems? Exercise set 1.1, numbers 2 and 11. Any questions about those two? Right, so for number 2, it said in each part, determine whether the equation is linear in x and y, right? So for instance, I am recording, okay. So for number 2, right, in each part, determine whether the equation is linear in x and y. Okay, so for instance, if you look at A is 2 raised to the 1/3 x plus the square root of 3y is equal to 1. Okay, and so the question is whether or not this equation is linear in x and y, and the answer is yes, it is. So you probably look at the exponential sign and you look at the square root and you'd say, no, it isn't. But x and y themselves are not in square roots. They're not raised to a power other than 1. 2 to the 1/3 is a constant. Square root of 3 is a constant. And so that is an equation. That equation is linear in x and y. So yes, it is linear in x and y. So that's an example of something from number 2. Okay, and number 11. You have to solve the linear system. Okay, and it says more. Solve the linear system if possible, and use the result to determine whether the lines represented by the equations in the system have 0, 1, or infinitely many points of intersection. Okay, if there's a single point of intersection, give its coordinates, and if there are infinitely many, find parametric equations for them. Okay, so solve the linear system. Find and all of that, right? So let's do that. Okay, so let's just do part A. So for part A, you have linear system 3x minus 2y is equal to 4, and you have the linear equation 6x minus 4y is equal to 9. And so now, now let's solve it. So add -2 times the first equation to the second to get, so your first equation stays the same. 3x minus 2y is equal to 4. And then the second equation, if you take -2 times the first and add to the second, you have -6x plus 6x cancels. -2 times -2y is 4y. 4y plus -4y is 0. Y. And so 0 to the left side. And then -2 times 4 is -8. -8 plus 9 is 1. So you get 0 equals 1 for the second equation. Okay. So now this system has the same solution set as this one. But the second equation is 0 equals 1. Okay. So the second equation is always false. So what does that mean? So that means that there is no assignment of values to the unknowns in the system that would make both equations true, since the second one's always false. And so that means the solution set there, that means the solution set is empty, right? There are no solutions, or there are no solutions. Okay, and so the linear system has no solutions. Okay. The first equation is a line in the XY plane. The second equation is nothing, right? 0 equals 1 has no solution. And so that means if you express it geometrically in the XY plane, it's just nothing. And so the intersection of a line and nothing is, well, nothing, right? And so the intersection of a line and nothing is nothing, okay? So there are no points of intersection between the geometric representation of the first equation and the geometric representation of the second one. And so that's part A of number 11. Okay. Maybe just to do one more, let's do B. So for B, you have 2x minus 4y is equal to 1. And you have 4x minus 8y is equal to 2.
Mother love me long time, long time. Sucky, sucky, fucky, fucky, one ton, Hong Kong, Hong Kong. One ton, Hong Kong, one ton. One time, one time, one ton. Love me long time, feet of my long schlong. Go back to Hong Kong, Terra, one ton, love me. Mother love me long time, long time. Sucky, sucky, fucky, fucky, one ton, Hong Kong.
Well, Professor Panda AS, I'll be damned at what I just saw. I ain't no cringy. Don't let me get Ralph. Ralph, stop picking your boogers. Ralph, don't put your poop in your ass. Ralph! Professor Panda AS, what happened?
Let's keep going. All right, so you have that linear system. And so if you add -2 times the first equation to the second, you get this linear system. So you get, so the first equation stays the same. 2x minus 4y is equal to 1. And then if you add -2 times the first to the second, you see that the -4x plus 4x cancels and the 8y minus 8y is 0. And so -2 plus 2 is 0. So you get 0 equals 0 for the second equation, right? And so okay, so tell Sabrina to come back. She can just request to come back into the room and I can sign her back in. That's fine.
I think if you kick someone out, they can come back in for the rest of the day.
Okay, can anyone talk to her? Can anyone email her? Anyone know her email to email her? All right, so I guess I'm going to waste class time on this. All right, so what's the student's name? Terry Zhao, can you turn on your video? Okay, so Sabrina, I'm letting back into the room, if that's the real Sabrina. Whoever Sabrina is, if this is really Sabrina. Okay. So Terry, can I see you in the can everyone turn your videos on? I'm not saying it's anyone at this point. I'm just, I haven't caught anyone doing it. Okay, so I just want everyone on their video. Okay, thank you. That way, if somebody does it again and I spot that person, then I know what the person looks like. Okay. So, okay, it's a requirement, right, for taking classes that you have audio and video that works, Cody. So you have to have a working video. But if, you know, another day. Okay. Okay, well, try to get video that works, because it's also good to participate and have video, even for any class, not just this one. All right, so Shelly, are you back in the room? Sabrina, Shelly, can you turn your video on? Everyone turn your video on. I'm not blaming you, Shelly. I'm just, Sabrina, I'm just asking you to turn your video on so I can just see everyone. Okay.
Professor, can you hear me?
I see you. Okay, you're good. I see you. You're good. All right. But
Okay,
yeah, there's some other people with their video, with their screens off. Okay, so I understand that somebody would put somebody else's name there, so I'm not reaching the conclusion.
I'm so pissed, Professor. I don't know why this happened. Like,
no, it's fine. It's fine. I didn't even think it was you. You know, they're not putting their name on it. I get that.
yeah, of course.
All right. Yeah, just make sure to have your first and last name on it when you sign in, and we'll just go from there. Your first and last name is clearly there. The other person used an account where it was your name, but then it had like other symbols on it. So don't have other symbols. Just your name. Okay.
Okay, got it.
Yeah. All right. All right. I didn't think this would still be a problem, but I guess it is. So I guess I'm gonna have to like. This is going to take, I'm going to have to do something about this. All right. Anyway, let's go back to the lesson. So you got back in the room, so everyone's fine. Okay, good. Okay. So, all right. All right, so, okay, so you have this linear, you can see this on the screen, I think. Okay, so, okay, so you now have this linear system, 2x minus 4y equals 1 and 0 equals 0. The second equation is always true. It's the opposite of the last problem. So if the second equation is always true, that means it doesn't do anything to the solution set of your system. And so you can remove it, okay? So since the second equation is always true, we can look at the smaller linear system consisting of just one equation, this one. Okay, so your linear system is now just one equation. So this one equation has the solution set to this one equation is the same as the solution set to the original linear system consisting of two equations. And so now you have as a solution set an entire line in the XY plane, okay? So the solution set of the system is represented geometrically as a line in XY space, okay? To express the solution set algebraically, we use parametric equations. Okay, so if you wanted to represent geometrically, you could draw a line, and if you want to represent it algebraically, you would use parametric equations. So to do that, let x equal t, let's say, and then I'm going to let so then that means that y is going to be equal to, so x is going to equal t, and now y, well, this equation 2x minus 4 equals 1, if you solve for y, Okay, well, let me just put as a note. Note, solving for y, you get that y is equal to 2/4 x minus 1/4. Okay, so if you bring the 4y to the other side, you get 4y equals 2x minus 1. And so divide both sides by 4, and you get y is equal to 2/4 x minus 1/4, right? Does that make sense? So you're just solving algebraically for y. That's equal to 1/2 x minus 1/4. Okay. Here. Okay, so then, so if we let x equal to t, then y is just equal to 1/2 t minus 1/4, right? Because, or let me just write this simpler, y is equal to 1/2 x minus 1/4. Okay, so that's our equation for y. That's solving for y in terms of x. And so if we let x equal to t, y is equal to 1/2 t minus 1/4. And so these are the parametric equations for the solution set of the system. Okay, so those are the parametric equations describing the solution set of the linear system. Okay. Okay, and so that's the solution to 2b. I mean 11b. Okay, so it's 11a and 11b. And okay, so that's good with the homework. So now, okay, chat. You could do that too. You can set y equal to t, and then plug in t, y equals t for the equation for x. You could do it either way. Okay. You're welcome. Okay. Good. Okay. And okay, so let's keep going. Okay, so at the end of last class, we left off with, okay, so we ended last class here, right? So I gave examples on matrices in row echelon form. Okay, good. Okay, so I defined for you what it meant for a matrix to be in reduced row echelon form. Alejandro, and okay, that's someone in the class. Okay, so, right, so I defined reduced row echelon form, right? So if a matrix has these 4 properties, it's in reduced row echelon form, right? And if it has only the first 3 properties, it's in row echelon form, right? There's a lot of material, so you have to reread this in order to, reviewing this would just take a long time in class, right? These first 3 properties are for row echelon form. All 4 of them are for reduced row echelon form. Okay, and these were examples of matrices in reduced row echelon form and in row echelon form. All right, so that's where we ended last class. Okay, okay, so last class, we ended with the definition and examples of matrices in reduced row echelon form and matrices in row echelon form. Okay. Okay, so let's act. If by a sequence of elementary row operations, the augmented matrix for a system of linear equations is put in reduced row echelon form, then the solution set can be obtained by either by inspection or by converting certain linear equations to parametric form. Okay, so if by a sequence of elementary operations, the augmented matrix for a system of linear equations is put in reduced row echelon form, then the solution set can be obtained either by inspection or by converting certain linear equations to parametric form. Okay, so what that means is you take a linear system that you start with, right? And you look at its corresponding augmented matrix, right? Its corresponding augmented matrix is just another way of representing that linear system. It's just it's easier notation, so you don't have to write down all the equations. Okay, so you have its augmented matrix. If you get that matrix to reduced row echelon form, you either obviously see what the solutions are, or you look at the equations represented by that matrix and you express them in parametric equations. And those parametric equations describe infinitely many solutions to your linear system. Okay, but we're going to do examples, and then examples will hopefully illustrate this better. So let's look at example 3. And so this example is a unique solution. Okay, so we're going to use this process and we're going to get exactly one solution for a linear system. Okay, so what we're going to do is first we're going to suppose that the augmented matrix for a linear system in the unknowns x1, x2, x3, and x4 have been reduced, has been reduced by elementary row operations to the following. Okay, so if you have a matrix, I've now built a larger matrix. Okay, so we have this augmented matrix here. We have 1, 0, 0, 0, 3, 0, 1, 0, 0, -1, 0, 0, 1, 0, 0, 0, 0, 0, 1, 5. Okay, so we have this. Suppose the augmented matrix for a linear system in 4 unknowns has been reduced by elementary row operations to this matrix. Okay. So we're going right to the end. We have a linear system. We have its augmented matrix, right? We simplify it and we get it to this. Okay. And so we simplify it to this matrix. Okay. This matrix corresponds to the linear system, to the following linear system. So if we have x1 is equal to 3, we have x2 is equal to -1. We have x3 is equal to zero, and we have x4 is equal to 5. Okay, so here x1 is equal to 3, x2 is equal to -1, x3 is equal to 0, and x4 is equal to 5. And so And so that's it. So this matrix represents that linear system, and you can see the obvious solution is that these unknowns have these corresponding values. Okay, thus the linear system has one unique solution, namely x1 is equal to 3, x2 is equal to -1, x3 is equal to 0, and x4 is equal to 5. Okay, so one possibility is that, sorry, you have your linear system, you have its augmented matrix, corresponding augmented matrix. You take the corresponding augmented matrix, you get it to, using elementary row operations, you get it to reduced row echelon form. And then when you get to reduced row echelon form, it looks like something like this. And when you look at its linear system, you see that there's exactly one solution, and it's that, and you're done. Okay, that's one possibility. This is the easy route, right? Again, you have your linear system, you have its corresponding augmented matrix. Then you take that corresponding augmented matrix, you get it to reduce row echelon form using elementary row operations. That's a matrix that satisfies the 4 properties from the last lesson. And then that matrix represents a linear equation, linear system, which tells you what the solutions are, that one solution is to your original system. Okay, so the 4 properties, again, for a matrix to be in reduced row echelon form is that every non-zero right? Okay, so if a row does not consist entirely of zeros, then the first non-zero number is in the row is a 1. We call this a leading 1. Okay, so the first property again is if you have a non-zero row, the first non-zero entry is a 1, and it's called a leading 1 for that row it's in. 2, if there are any rows that consist entirely of zeros, they're at the bottom. Okay, if there are no entirely zero rows, then this condition is satisfied vacuously. Okay, 3, for any 2 successive rows that do not consist entirely of zeros, the leading 1 in the lower row is further to the right than the leading 1 in the one just above it. Okay, that's for any 2 successive rows that are non-zero rows. Okay, that's the third property. And the fourth one is every column that contains leading 1, everywhere else in that column other than where that 1 is, everything else is 0. So these are the 4 properties a matrix needs to be in reduced row echelon form. This matrix has all 4 of those properties. Every non-zero row has a leading 1. Every first non-zero entry in a non-zero row is a 1. See, every non-zero row has leading 1. That's property 1. Property 2, all the 0 rows are grouped at the bottom. There are no 0 rows, and so that's true vacuously. It's 2. 3, if you take any 2 successive non-zero rows, the leading 1 and the lower 1 is further to the right than the leading 1 above it. This is further to the right than this is further to the right than that, and this is further to the right than that. So property 3 is also satisfied by this in this matrix. Property 4 says any column with a leading 1, all the other entries are 0. So this is a leading 1, and it's in the first column, and every other entry is 0. There's a leading 1 here in the second column, every other entry is 0. This is a leading 1 here, every other entry is 0. And there's leading 1 here, and every other entry is 0. There is no leading 1 in the last column, and so you don't worry about it. So the first 4 columns each have their own leading 1s from those 4 rows, and that's true for all of them. So property 4 is also satisfied by this matrix. Okay, so you need to study those 4 properties and be able to distinguish and know when matrices have those properties and when they don't, and remember the 4 and be able to say, okay, I'm looking at a matrix, it satisfies all 4 properties, it's in reduced row echelon form. Or it satisfies the first 3, that means it's in row echelon form. Okay, but anyway, this matrix satisfies all 4 properties, and so it is in reduced row echelon form. Okay, and so that's the situation we're given in this example. That you have an augmented matrix, corresponding linear system. You take the corresponding linear system, corresponding augmented matrix, get it to reduced row echelon form, and you get this. Okay, and so then that represents a linear system, which obviously has exactly one unique solution. Okay, so that's that example. Another example. Example 4, linear systems in 3 unknowns. Okay. All right, you're in this class, I think. In each part, suppose that the augmented matrix for a linear system in the unknowns x, y, and z has been reduced by elementary row operations to the given reduced row echelon form. Solve the system. Okay. Okay, so we're skipping the steps in the procedure where you have to get these matrices to reduced row echelon form. So to learn this, we're starting with the fact that we already have the matrix in reduced row echelon form, and we just want to take that matrix and we want to find a solution set from it. Okay, so this is like the later step. We're doing the later step first and the earlier steps later. That's because the last steps are easier than the earlier steps. Okay, and so this is an easier step to understand. Okay, so that's why we're doing this first. So we have this matrix in reduced row echelon form. Okay, so you have that. So now let's look at one. I got to put in the entries 1, 0, 0, 0, 0, 1, 2, 0, 0, 0, 0, 1. Okay, so every non-zero row has leading 1, property 1. All the 0 rows are at the bottom, true vacuously. The leading ones in the lower row is for the right the one above it, right? That's true. Property 3. Property 4, every column with the leading 1 has 0s everywhere else. That's also true. Columns 1, 2, and 4 have leading 1s. And so those columns only have 0 entries everywhere else other than leading 1s. So this matrix satisfies all 4 properties of a matrix being in reduced echelon form. Okay. So we want to solve the system now, given that. Okay. So looking at the last row, it represents the linear equation, the following linear equation. I'll plug in the chart. Okay, so looking at the last row represents the linear equation 0x1, 0x plus 0y plus 0z is equal to 1. Right? 0x plus 0y plus 0z is equal to 1. But that means that the equation says that 0 equals 1, which is always false. So this linear system has no solutions. Okay, because the third equation has no solutions. That means that there are no solutions to all of them. Okay, so that's A. For B, we have another matrix. It's 3 by 4, same size as this one. So I'm just going to change the entries. 1, 0, 3, -1, 0, 1, -4, 2, and all zeros at the bottom. Okay, so this is the next matrix. Okay, so the third row represents the linear equation 0x plus 0y plus 0z is equal to 0. This equation is always true. That means it has no effect on the solution set of the linear system. Thus, we can exclude the third row or third equation and still have the same solution set. Okay, so now we only have to look at the first two rows of that matrix. And so we look at only the first two equations. So the first two equations are x plus 3z is equal to 0. And the second equation is y minus 4z is equal to 2. Okay. A little less space there. I don't need that much space. Okay. So we have x plus 3z equals -1. And y minus 4z is equal to 2. Okay, so now we want to find the solution set here. So first, note that x and y correspond to leading ones in the augmented, in the matrix above it, Okay, so this one corresponds with x, and this one corresponds with this y, but they're not just ones, they're leading ones. So these two leading ones correspond correspondingly to x and y. So that means that x and y are called leading variables. Okay, so just like you have leading ones in your matrices, you have leading variables in your linear systems. Okay, and so leading ones in the matrices correspond with leading variables in your linear system. Okay, the remaining variables are called free variables. Okay, so any variable that does not correspond with a leading one is called a free variable. So z does not correspond with a leading one, and so z is a free variable. Okay, so in this linear system, there is one free variable, namely z. Okay, so x and y correspond with leading ones, and so x and y are leading variables. Z does not correspond with a leading variable. The third column does not have a leading one in it, and so z is a free variable. Okay. Solving for the leading variables in terms of the free variables, we get x is equal to -1 minus 3z, and we get that y is equal to 2 plus 4z. Okay, so here Z is a free variable, right? And so we're going to express X and Y, which are the leading variables, in terms of Z. So X is going to equal to -1 minus 3Z. And then Y is going to equal 2 plus 4Z. So we've now expressed both leading variables in terms of the only free variable Z. Okay, so from these equations, we see that the free variable Z can be treated as a parameter. Okay. So let's assign Z equal to T. Okay. Here, T is the parameter. Okay. So we let Z equal to T, and so the solution set can be represented by the parametric equations. So X equals -1 minus 3T. Y is equal to 2 plus 4T. And Z is equal to T. Okay, so we let Z equal to T, the parameter T, and then since X and Y were solved in terms of Z, we just plugged in for ZT, and now we have an expression of X and Y in terms of only T. And so now these three are the parametric equations that describe the solution set of the original, of the linear system represented by that matrix. Okay, so the part that this plays in the larger problem is that you start with, again, I'm going to say the same thing again. You start with the linear system. You have its corresponding augmented matrix. You take this augmented matrix, you get it to reduced row echelon form. And then if it's a matrix like this in reduced row echelon form, you then look at its corresponding linear system. You may be able to get rid of a row if it looks like that. And so you look at its corresponding linear system, and then you express the solution set of, you might express the solution set of that linear system using parametric equations. Okay, right? And you'll see the difference. So if it looks, again, your matrix is now in reduced row echelon form. That's why you now can express it in parametric form. Okay, if your matrix was not in reduced row echelon form, you could not express it in this way. Okay, directly. So we're getting directly this because we've already gotten it to reduced row echelon form. That's how it enables us to do this. If you didn't first have it in reduced echelon form, you couldn't do this step right after. Okay, but if you have a matrix like this, you'd have it like that. In A, if you have a matrix like this, then you just see, okay, well, this was, I'm sorry. If you have a matrix like this, you see directly that there's just one solution, right? So you might have something like this. Is this one solution? Or you have something like this, infinitely many solutions. Okay, so there's a clear difference. And so you can see directly from the linear system corresponding to it, whether you're looking at one solution or infinitely many solutions. Okay. All right. And so now these are the solutions in parametric form. Okay. So okay, so now let's look at part C to this. So for part C, we have the matrix okay, and then everything else is the zeros. Okay, so now we have a matrix that looks like this. Okay, and this is in reduced row echelon form. It satisfies all four properties. The only non-zero row is leading one. All the zero rows are at the bottom. Every column with a leading one has zeros everywhere else in that column. And any two consecutive non-zero rows, leading one in the lower one is further to the right than the one above it. that's true vacuously because there are no two consecutive rows that are non-zero. There's only one row that's non-zero. And so property 4 is satisfied vacuously. Okay, so this matrix satisfies all 4 properties for a matrix to be in reduced echelon form. So we have a matrix in reduced echelon form, and we just want to find the solution set that from that. Okay, so as explained in part A, in part B, we can omit the equations corresponding to all 0 rows. Okay, so the second and third rows are just all zeros. And so those correspond with equations 0 equals 0. And so we can just omit them because they don't change the solution set at all with or without them. Okay, so we're left with one equation represented by the first row of that matrix. Okay, so that leaves us with only the first row, which represents the equation x minus 5y plus c is equal to 4. Okay, and so this equation is represented geometrically by a plane in 3 space. Okay, so if you have 3 unknowns here, and so it's represented geometrically by a plane in 3 space, and we can express that using parametric equations again. We have one leading variable x and 2 free variables y and z. Okay, so here, if you're only looking at this one row, the 1 and the x corresponds with the leading 1 here, right? So x is a leading variable. There's only one leading 1, and so that means there's only one leading variable, and so everything else is a free variable. So y and z are free variables. Okay, so when you express this in terms of parametric equations, each separate free variable has its own parameter. Okay, so note that each free variable has its own distinct parameter. Okay, assigned to it. So let y equal to the parameter s and z equal to the parameter t. Okay, so I chose s because s and t are next to each other. So, and y came first, so s comes first. Okay, so let y equal s and z equal t. Those are our parameters. Okay, then the parametric equations that describe the solution set of this linear system are x, if you solve for x, you get let me just put a note here. Sorry, if we solve for x, solving for x, we get that x is equal to 5y minus z plus 4. Okay, so the parametric equations that describe the solution set of this linear system are, well, x is equal to 5 times y, which is s, minus z, which is t, plus 4. So that's x. And then y is still equal to s, because that's the parameter assigned to it, and z is equal to t. And so these are the parametric equations. These are the parametric equations describing the solution set of this linear system. Since your linear system has one equation and since your linear system has one leading variable and 2 free variables, that means you have 2 parameters, one for each free variable. And so you have two parameters, and now the leading variable is expressed in terms of those parameters. Okay, and then all the free variables are just given assigned a parameter. So y, z are free variables. They're each assigned a parameter. X is a leading variable, and you express it in terms of the parameters, s and t. Okay, and so now we've expressed the solution set of this linear system again by parametric equations. Okay, so we either got one distinct solution that we got right away from the matrix, or we had a system that we could express using parametric equations, which express the solution set. Okay. Any questions about all this? This can all be a bit confusing at first. This is a lot to take in. There's a lot of different things happening. I think the best way is to just be immersed in it and just keep seeing what we're doing and practicing it, and it starts to make more sense. Okay, so there's a lot of weird stuff going on. One day it all starts making sense. Okay, so let's keep going. Okay, so so let's go over some terminology. Okay, so definition 1. If a linear system has infinitely many solutions, then a set of parametric equations from which all solutions can be obtained by assigning numerical values to the parameters is called a general solution of the system. Okay, so definition 1, if a linear system has infinitely many solutions, then a set of parametric equations from which all solutions can be obtained by assigning numerical values to the parameters is called a general solution of the system. And so this is a general solution of the system. Okay, there are parametric equations that represent the infinitely many solutions of a linear system. Okay, and so for each different assignment of parameters s and t, you get a different distinct solution of the system, right? So if I assigned s to be 1 and t to be 2, then I would get a corresponding value of x, and those values of x, y, and z would satisfy every equation in the original linear system. Excuse me, sorry. If I assigned s to 100 and t to 1,000,000, and I plugged that in for x, then the x, y, and z there would also be another distinct solution of the original linear system. Okay, so I can assign any values I want to s and t because they're parameters. Any real value I want. S could be the square root of pi, t could be the cubed root of 3,000,000, and then you plug s and t, those values, into x there, and then the x, y, z would be another solution to the linear system. Okay, so there's infinitely many solutions because there's infinitely many choices you have for both s and t. And so there's infinitely many possibilities for what x, y, and z could be that satisfy these three equations. Okay, so, but anyway, these three equations is what's called the general solution of the system. Okay, not a particular solution, right? If you plug in values, you only get one solution, right? But you want infinitely many. And so you can't write out infinitely many solutions one at a time. And so the only way you can do that is by expressing it generally. So we express the infinitely many solutions generally by these three equations. Okay, so that's a general solution of the system. Okay. Okay, next, let's go over elimination methods. Okay, so now we will go through a step-by-step elimination procedure that can be used to reduce any matrix to reduced row echelon form. Okay. Okay, so what we've already done is look at a matrix in reducible echelon form and either see the unique solution from it or the parametric equations from it, right? Before that, the step preceding it is we need to get our augmented matrix to reducible echelon form. And so in order to do that, we have these elimination methods that works generally. So for given any matrix, you apply this procedure and you get it to reduce echelon form, okay? Every matrix can be reduced by only elementary row operations to a matrix in reduced echelon form, okay? So that will always happen for any matrix, okay? Okay, so what we're gonna do now is we're gonna take a matrix, we're gonna start with the matrix, and the goal is going to be to get it in reduced echelon form, okay? So now we start with a matrix and get it to reduced row echelon form using an elimination method. Okay. So let's look at this matrix here. All right. All right, so it's a 3x5 matrix. Oh, I want 3x6. Okay, 3x6. Okay, so now I'm just going to plug in the entries. So you have 0, 0, -2, 0, 7, 12, 2, 4, -10, 6, 12, 28, 2, 4, -5, 6, -5, and -1. Okay, so we're going to start with this matrix here. Okay, so I think I'm going to move to the whiteboard, which I avoid doing, but I'm going to go to the whiteboard. Okay. Let's see. It takes too long to type it. Okay, so we're going to start with that matrix though. So maybe, okay, so move things around on my screen. Okay. So let's start with this 0, the same matrix I have there. I'm copying it down again. Yeah, I'll try to write this so that you can see it easily. Okay. To 12. I'm going to put a vertical bar there because that's separating the variables and with the numbers at the end of the equation. Okay. So for step 1, okay, so for step 1, I can still type here. So for step 1, we're going to locate the leftmost column that does not consist entirely of zeros. Okay, so we want to locate the leftmost column that does not consist entirely of zeros. Okay, so that's this column right here, right? but I had a color here and it disappeared. Okay, there we go. Okay, so this is the leftmost column that does not consist entirely of zeros. Okay, and so we located it, and so we're good there. So step 2. Step 2. Interchange top row with another row, if necessary. Bring a non-zero entry to top of the column found in step 1. Okay, so in step 2, we want to interchange the top row with another row, if necessary, to bring a non-zero entry to the top of the column found in step 1. Okay, so the problem with this first column, in the column that I have circled in blue, is that the top entry of that column is 0. We want a non-zero entry there. And so what we're going to do is we're going to switch the first and second rows. And by switching the first and second rows, we're going to have a non-zero entry at the top of that column, okay? Right now it's a 0. We switch the first and second rows, we then have a non-zero entry at the top of the column. And so that's step 2, okay? So I'm going to do that here. So now I'm going to write this matrix out. And so this matrix is the result of switching the first and second rows. So first, the last row stays exactly the same. I oftentimes like to look at the easiest thing first. The third row stays the same. If I switch the first and second row, the first row is now was the second row before. So you have these entries here, right? So these are the entries from the second row, which is moved to the first row. And now the first row is now the second row. And so now I'm just writing the second, I'm just writing what was the first row as the second row. Okay, so now I've now switched the first and second row, and I now have it here. Now, the first column, the first non-zero column is now has a non-zero entry at the top of the column. Okay, so that was the goal. To bring a non-zero entry to the top of the column found in step 1. So we now have a non-zero entry at the top of the column found in step 1. Again, step 1 was the leftmost non-zero column. And then step 2, you switch rows so that the top entry is now a non-zero entry. If you have to. If it's already non-zero, you just skip step 2. It's already done. Okay, now step 3. I'm going to put the words here, and then I'm going to have to draw the matrix on the next slide. Okay, but step 3 is going to be okay, so step 3 is if the entry that is now at the top of the column found in step 1 is A, multiply the first row by 1 over A in order to introduce a leading 1 for that column, in order to introduce a leading 1. Okay, so what's happening here is that this entry is a 2 at the top now. It's non-zero, but it's 2. We want it to be a 1. And so we're going to multiply this row by 1/2, 1 over 2. So since there's a 2 here, we're going to multiply the first row by 1 over that number, 1 over 2, and then 2 is going to become a 1. And so now we have a 1 at the top of the leftmost non-zero column, okay? So we're in the beginning, we first located the leftmost non-zero column. In the beginning, we had a 0 at the top. And so in 2 steps, we're going to have that top entry, instead of being a 0, it's going to be a 1, okay? Okay, so that sums up the first 3 steps, making the top entry of the leftmost non-zero column a 1. Okay, so on the next screen, I'm going to go to the next slide. I'm just going to rewrite this matrix here, except the top row is going to be multiplied by 1/2. Okay, so all I'm doing is I'm multiplying the top row by 1/2, and there'll be a 1 there. Okay, so that's all that's happening in the new slide. Okay, so now we have so we have 1, 2, -5, 3, 6, 14. And then the next row is 0, 0, -2, 0, 7. And that's 12. It's 2, 4, -5, 6, -5, -1. Okay? Okay, so I multiplied the first row by 1/2. And so now we have this matrix. Okay? And so this leftmost non-zero column, this was the leftmost non-zero column from before that we located. And this was the top entry, which was a 2. Now it's a 1. Okay, so now we have the topmost entry in the leftmost non-zero column as a 1 in the first 3 steps. And so now let's do step 4. So step 4 says the following. Add a suitable multiples of the top row to the rows below, so that all entries below the leading one become zeros. Okay, so we're going to add suitable multiples of the top row to the rows below, so that all the entries below the leading one become zeros. So we have a leading one at the top of this column we've now selected, but not all the entries below it are 0. This entry is 0, so we just move on from there. But this entry is a 2, which is not 0. So the goal now is going to be, let's make sure that everything that's non-zero in this column becomes 0. So what we're going to do is we're going to now add a suitable multiple of the first row to the third row to make it 0. Okay? And so what we're going to do is we're going to have to add -2 times the first row to the third row to make it 0 in this entry here. And so we're going to do that. Okay? And so in step 4, we do that. Okay, so now we're going to add. So this is for this particular problem. It's not a step. The steps are the steps in the general procedure. What I'm writing here is just for this particular problem, explaining it for this problem. I'm adding -2 times the first row to the third row. Okay, so I'm adding -2 times the first row to the third row. And then what we get is the result of that. So the first row stays the same. The second row stays the same. And so since we're adding -2 times the first row to the third row, it's the third row that changes. And so if you take -2 times this and add to this, you get 0. -2 times 2 is -4. -4 plus 4 is 0. -2 times -5 is 10. 10 plus -5 is 5. -2 times 3 is -6. -6 plus 6 is 0. -2 times 6 is -12. -12 plus -5 is negative 17. And then negative 2 times 14 is negative 28. Negative 20 plus negative 1 is negative 29. So now we get those numbers there. Okay, and so now this is the leftmost. This was the leftmost non-zero column we selected in step 1. The one at the top was the one we made there. But now we have only zeros everywhere else, right? So now this entry has become a 0. And so we succeeded in step 4 to make all the entries below this leading one all zeros. And so now we have our leftmost non-zero column in the way we want it. It's at the top is a 1 and everything below it is a 0. Okay, so that's step 4. And so there's 2 more steps. So now here's step 5. Step 5. Now cover the top row in the matrix and begin again with step 1 applied to the submatrix that remains. Okay, so what's going to happen is you cover up the top row. Okay, so I'm going to choose, oh, not that. We're going to cover up the top row. I'm going to do that. Right. So we're going to, that top row there, we're going to cover up, and then we're going to look at everything else as the submatrix, and we're going to restart at step 1 with that submatrix. Okay. I have more to type. Okay. Continue in this way until the entire matrix is in reduced is in row echelon form. Okay, so we're going to, after step 4, we take the row that one was in and we cover it up. And then we look at the rest of it as a submatrix. Okay. Okay, so what's going to be covered up okay, so now we're going to look at this as our submatrix in the orange. See the 2 rows below it? That's going to be our submatrix. So the submatrix that remains is the second and third row. We covered up the top row, and we're going to look at the second and third row as a submatrix. And so the top row of the submatrix is going to be the original second row. Okay, the row is 0, 0, negative 2, 0, 7, 12. That's the top row of our submatrix. And so we're going to start again at step 1, considering that as the top row. Okay, and the leftmost non-zero column is not this anymore because we're looking at the submatrix. The leftmost non-zero column is negative 2, 5 here. Okay, so we then go back to step 1 for the submatrix. We repeat all the steps 1, 2, 3, 4. Then we get to step 5, and then we cover up the top row again. Okay, and so we keep repeating the first 4 steps until when we get to step 5, we have a matrix that's in the entire matrix, not well, including the rows we covered up. The entire matrix is in row echelon form. Okay, so we do steps 1 through 4, and then step 5 we cover up the top row, and then we go back again. Steps 1 through 4, cover up the next top row, then repeat again. Steps 1 through 4, step 5 cover up the top row, and we keep doing that until in step 5. When we're going to cover up the top row, we say, wait, the entire matrix is in row echelon form. When that happens, instead of going back to step 1, you move on to step 6. Okay? So now I'm going to do step 5, because after you cover up the top row, well, this matrix is not in row echelon form, okay? Not every non-zero row has a leading 1. The first row has a leading 1, but the second row doesn't. And so right away, this fails property 1 of a matrix being in row echelon form. Row echelon form is satisfying the first 3 properties, right? Reduced row echelon form is satisfying all 4. So we're looking for a matrix to satisfy the first 3 properties. And this matrix fails the first property. Every non-zero row has to have a leading 1, but this doesn't. And so since it's not in row echelon form, we cover up the top row and we go back to step 1 and repeat the procedure. Okay, so let's do that. So I'm going to take this matrix, cover up the top row, and begin again in step 1. But technically, I'm in step 5, the step of, well, no, okay, I'm back in step 1. Okay, so I'm now covering up the top row. Okay, so I'm going to type that in. Okay. Okay, so we now go back to step 1 since so we now go back to step 1 since the matrix was not in row echelon form. Okay, we can see that it is not in row echelon form since it fails the first property. Not every row has a leading 1. Specifically, neither the second nor third row have a leading 1. Okay, so the matrix is not in row echelon form, and so we go back to step 1. We also cover up the topmost row. Okay, so we cover up the topmost row and we go back to step 1. Okay, it's important to know what's happening in step 5 as we do it. Okay, so our matrix is 1, 2, -5, 3, 6, and 14. That's the first row of the entire matrix from the beginning after it's been reduced from the first 4 steps. So we have this matrix here. Okay. And so we're covering up the top row. So let me cover it up with I'm gonna use orange. Okay, so I'm gonna cover it up with orange. Okay, so I've now covered up the top row. Okay, so this row is covered up. Covered up top row. Okay. So now we're looking at only this one. So now repeat with step 1. Well, step 1 was locate the leftmost non-zero column. So step 1 is locate the leftmost non-zero column. And I'll even go back to where I wrote it. Step 1, locate the leftmost column that does not consist entirely of zeros. So that's the leftmost column in the submatrix that does not consist entirely of zeros. Okay. So step 1, check. Okay, step 2, interchange the top row with another row if necessary to bring a non-zero entry to the top of the column found in step 1. We want the top entry to be non-zero. The top entry is non-zero. And so step 2 is done. We don't have to do anything in step 2. Okay, so step 2 is also done. Step 2 is done because the topmost entry is non-zero. Okay, so without doing anything, step 2 is good. And then So then we go to step 3. Step 3 says if the entry that is now at the top of the column found in step 1 is A, the letter A, multiply the first row by 1 over A in order to produce a leading 1. So here, this entry is -2. So you multiply that row by 1 over -2. Okay? And so when you multiply that row by 1 over -2, you get a 1 in that entry. Okay? If it's already a 1, you don't have to multiply it by 1 over 1. It's just, you just leave it wrong. Okay, so we're going to now do step 3. And we're going to multiply that topmost row by 1 over -2. Okay, so steps 1 and 2 are done. To do step 3, we multiply the topmost row of the submatrix by 1 over -2 to introduce a leading 1. Okay, so by multiplying this row by 1 over -2, we introduce a leading 1 there where there wasn't one, right? We want every row, non-zero row, to have a leading 1, and so we need a 1 there to have a leading 1. It's a leading 1 because it's the first non-zero entry, and so when it's a 1, it's leading 1. Okay. So now, so we have the top row was covered up. It's still covered up. We're multiplying this row by 1 over -2, which is -1/2. So 1, that's -7/2. This is -6. The third row stays the same. Okay, so now the first row is still covered up. And the leftmost non-zero column is there. Okay, and the topmost entry is now leading 1. Okay, so now step 3 is now also done. Okay, so now we're done with step 3. When doing step 3 again, because we're repeating, right? Now, it's step 4. We want all the entries below this leading 1 here to be 0. And so this 5 is no good because it's not, it needs to be 0 and it's not. So we need to add a suitable multiple of this row to this row to make this a 0. So we're going to add -5 times this row to this row to make that a 0. Okay? And keep in mind, all the operations I'm doing, algebraic operations, are elementary row operations. Okay, so -5 times this row plus this one. And so after we do that, we get the following matrix. So okay, so we get 1, 2, -5, 3, 6, 14, 0, 0, 1, 0, -7/2, -6. These first 2 rows are exactly the same. And then this row is after adding -5 times the second row to the third row, or the topmost row to the lower one, the submatrix. Okay. Because you get this. Okay, so this again is the covered up topmost row. This was the leftmost non-zero column. This is the leading 1 we introduced at the top of that column. And this is the entry that used to be non-zero, which is now 0, because we added -5 times this row to this row to get this. Okay. So here, right? So, okay. So, we. Oh, there we go. Okay, above we added, I'll make this red. Above we added negative 5 times the topmost row of the submatrix. I'm writing more than I have to, but so it makes sense. So above we added negative 5 times the topmost row of submatrix to the bottom row to get only zeros below the leading one in the column from step 1. Okay, so now we have this. Well, now we have only zeros below that leading one there. Okay, and so now that we've done that, we're done with step 4. Right, so step 4 was that, so that everything below Z. Step 5 is now cover the top row of the matrix and begin again with step 1, apply to the submatrix that remains. Continue in this way until the entire matrix is in row echelon form. Okay, so now we are back to step 5. If the matrix we currently have is in row echelon form, then we can move on to step 6. Okay, so we look at this matrix as we have it currently, and we want to see, is this matrix in row echelon form? Well, the first property is that every non-zero row has leading 1. The first row has leading 1, and the second row is leading 1. But the third row does not have leading 1. The first non-zero entry is 1/2. Excuse me, not 1. And so this matrix is not in row echelon form. Okay, but this matrix is not in row echelon form because the third row is a non-zero row and it does not have a leading 1. Keep in mind, it has a 1 in the row, but it's not a leading 1. A leading 1 is the first non-zero entry. That's the one that has to be 1. And even if there's ones after it, it doesn't matter. It doesn't change the fact that it doesn't have a leading 1. Okay. But this matrix is not in row echelon form because the third row is a non-zero row and it does not have a leading 1. The first property says every non-zero row has a leading 1. So finding one row that's non-zero that doesn't have a leading 1 means that it's false to say that every row, non-zero row, has leading. Okay, this matrix is not in row echelon form, so we cannot move on to step 6. Okay. Okay, so since we do not have a matrix in row echelon form, we go back to step 1 and repeat the procedure again from there. Okay, so now we're going to go back to step 1 again. Okay, now, since we do not have a matrix, we go back to step 1 procedure again. We also cover up the topmost row of the submatrix. Okay, so now we're going to cover up the topmost row of the submatrix, and so I'm going to write that here. Okay, good. Okay, so the top, we already covered up this row. Now we're going to cover up again the topmost row of the submatrix. And before we move back, go back to step 1. So now we've covered up the next topmost row of the submatrix. And so now the submatrix is only this bottom row. Okay, so we're going to go back to step 1 with now only this bottom row considering. Okay, so let's go do that. Okay, so so you have 1, 2, -5, 3, 6, 14, 0, 0, 1, 0, -7/2, -6, 0, 0, 0, 0, 1/2, 1. Okay, so I'm rewriting these things again because I just want to move slowly, so that way I'm hoping that you can get this. Okay, so, right, as much as can the first right now. So I cover up the top 2 rows, and the submatrix is now only this row, right? But I'm going to start again with step 1. So in step 1, way back in the beginning, locate the leftmost column that does not consist entirely of zeros. So now the submatrix is only this one row. So the leftmost non-zero column is this individual entry 1/2. That's the leftmost non-zero column. So step 1 is done. Next, step 2, interchange the top row with another row if necessary to bring a non-zero entry to the top of the column found in step 1. We want a non-zero entry at the top of this column that we selected. It's already non-zero. And so it's also the green entry. So now step 2 is also done because the topmost entry is non-zero. It's the only one, and it's non-zero. That's step 2. Okay, so step 2 is done. Step 3 is if the entry that is now at the top of the column found in step 1 is a multiple, is A, multiply the first row by 1/A in order to introduce a leading 1. So we want that to be a 1. So we multiply it by 1/1/2. That means multiplying it by 2. Okay, so now step 3, what we see is that, okay, good, it's green and red. So now this is also the red, everything. This is also not, this is not a 1. So we want it to be a 1. So what we're going to do is we're going to multiply the row by 1/1/2, which is equal to 2. Okay, so we're going to multiply this row by 2, or 1/1/2, 1/A. A is 1/2, so multiply by 1/A, that's 1/1/2, which is 2. Okay, so now we multiply it by 2, that row. So we have 1, 2, -5, 3, 6, 14, to 6, 0, 0, 1, 0, -7/2, -6. Now this is going to be the row after we multiply it by 2. Now we get that. Okay, so now this is the row we covered up. This is the other row we covered up. This is the column we selected. This is the topmost entry of the column we selected. And this is, it wasn't a 1 and now it is 1. Okay, so now we have a 1 there. So now the first non-zero entry is a 1. So we now have a leading 1 there. Okay, so now step 3 is done. Step 3 is done. So now step 4, add suitable multiples of the top row to the rows below so that all entries below the leading 1 become zeros, right? So we want all the entries below this leading 1 to be zeros. Like here, there's all zeros after this step. And then here, there were all zeros below this after that, right? But here, there's only one entry in this column, and it's a 1. So there's nothing below it. And so the goal is to have all the entries below it 0. And since there are no entries, that means we're done already. So step 4 is done without doing anything. You don't have to do anything for step 4 right now in this particular moment in time. Step 4 is not needed because there's only one entry. So step 4 is now done. So now we're done with the 4 steps again. So that means we move on to step 5. And so remember, step 5 is now cover the top row in the matrix and begin again with step 1 applied to the submatrix that remains. Continued in this way until the entire matrix is in row echelon form. So the question is the matrix in row echelon form? Hope so, because there's nowhere else to go. So let's see, is this entire matrix in row echelon form? Every non-zero row has leading 1. This is leading 1, this one, and this one. So property 1 is satisfied by this matrix. Property 2 is that all the 0 rows are at the bottom. There are no 0 rows. And so property 2 is also satisfied with this matrix. Property 3 is that for any 2 consecutive non-zero rows, the leading one, the lower one, is further to right than the leading one above it. This leading one is further to the right than this one. This leading one is further to right than that one. So property 3 is also satisfied by this matrix, okay? And then property, well, that's it. So, sorry, 3 properties for row echelon form. So this matrix is in row echelon form. And so that means we can move on to step 6 finally, okay? This matrix is in row echelon form because it satisfies all 3 properties for a matrix to be in row echelon form, as can be checked. Okay. So this matrix is now in row echelon form, and that means we are done with step 5 and move on to step 6. Okay, so we no longer have to go back to step 1 after step 5. We now can move on to step 6 because our matrix is now in row echelon form, and no previous point in time was it in row echelon form. Okay, so let's go to the next slide. Okay, so the entire matrix is now in row echelon form. To find the reduced row echelon form, we need the following additional step 6. Okay, so the first 5 steps were to get the matrix in row echelon form for it to satisfy the first 3 properties. So 5 steps were needed to satisfy 3 properties. The 6th step is for the matrix to satisfy the 4th property, which means that it's also now in reduced row echelon form. Okay, so that's why we have a step 6, because we only have a matrix in row echelon form and we want a matrix in reduced row echelon form. Okay, so step 6 is following. Beginning with the last non-zero row and working upward, add suitable multiples of each row to the rows above to introduce zeros above the leading ones. Okay, this is step 6. Beginning with the last non-zero row and working upward, add suitable multiples of each row to the rows above to introduce zeros above the leading ones. Okay, so up until this point, we were working up to down. Now we're going to, in step 6, only step 6, we're working from down to up. Okay, so good. Okay, so now we have this matrix. See, okay, so let me. I'm going to rewrite again the matrix we already have. Work from that. So we have 1, 2, -5, 3, 6, 14. 0, 0, 1, 0, -7/2, -6, 0, 0, 0, 0, 1, 2. Okay, so this was the matrix at the end of step 5, right? And it's in row echelon form. Okay, so this step 6, we're going to work from the bottom up, beginning with the last non-zero row. Okay, so beginning with the last non-zero row and working upward. So the last non-zero row is this guy right here. Okay, add suitable multiples of each row to the rows above to introduce zeros above the leading ones. Okay, so we have a leading 1 here. And so we want zeros, for every entry above it. This is the leading 1 for the bottommost row. And the entries above it are not all 0. In fact, none of them are. And so we're going to add suitable multiples of this last row to the rows above it so that those red entries, the entries above that leading 1 in that row, become 0. Okay, so now the result is going to be that there's going to be only zeros in columns with leading 1s. That's the fourth property. The fourth property says every column with a leading 1 has zeros everywhere else, right? And so if we have a leading 1 here, the column that it's in has to have zeros everywhere else. And so if it doesn't, we just need to add suitable multiples of that row to the other rows so that they become 0. Okay, so that's what we're going to do here. Okay, so now we add 7/2 times the third row to the second, and also add -6 times the third row to the first to get only zeros above the leading 1 circled in green. Okay, so we're going to take 7/2 times this row and add to this row, and then take -6 times this row and add to the first row. That way there's only zeros above this leading 1. Okay, so the bottommost row is 0, 0, 0, 0, 1, 2. And so if you take 7/2 times this row and add to this one, you have 0, 0, 1, 0, because these are all zeros. So adding 7/2 times these zeros to this doesn't change it. Then 7/2 times 1 plus -7/2 is now 0. And then 7/2 times 2 is 7. 7 plus -6 is 1. So you get a 1 there. Okay. So this is the bottommost row from just above. This is the leading 1. This is the -7/2, which is now at 0 because I took 7/2 times the third row and added it to the second. Now I'm going to take -6 times the third row and add it to this first. -6 times this row and add to this one, so that's 0. So now, since the first 4 entries are 0, it doesn't change these first 4 entries. See that? So these first, it doesn't change it. And then -6 times 1 is -6. -6 plus 6 is 0. And then -6 times 2 is -12. -12 plus 14 is 2. There's a 2 there. Okay. And so now this is the other entry that was a 6, and now it's a 0. And so now this column is now only consisting, everything other than the leading 1 in that column is now only zeros. See that? And so that was the change. Okay, but we're not done with step 6. So it's the beginning with the last row and working upward. So now we need to work upward. And so if we're working upward means we started with the last row, with the last non-zero row. Working upward means we now look at the next non-zero row. And so I'm going to go to the next page. What we're going to circle is going to be this row. This is going to be the row that's the working upwards. Okay? So I'm going to continue that next screen. And so we're almost done. Okay. 0, 0, 0, 0, 1, 2. 0, 0, 1, 0, 0, 1, 1, 2, -5, 3, 0, 2. Okay, so this was the last non-zero column. This green, green, red, red, light pink. There's that. Just checking. Okay, good. Okay, but now we're going to work upwards, right? So I labeled the working upwards with a brown underline, and so recognize that that's this row. We started with the bottom row, and we added suitable multiples of it so that all the entries above the leading one in the bottommost row become zeros. Working upward, we now go to the next row just above it. And now we look at the leading one in that row. And then we say, okay, are all the entries above it 0? Or every entry everywhere else in that column 0? Since we're working upward, everything below it, if we're doing things correctly, should already be 0. So there is a 0 below it because we're working upward. So the only thing we need to care about in step 6 are up. And so this entry may or may not be 0. In this case, it's not 0. And so we need to add a suitable multiple of the brown row to the top row so that becomes a 0. And so that all the entries in this pink column, which contain this leading one for this brown row, that all the other entries are 0. Okay, so add 5 times the brown row to the top row to get a 0 there. Okay, now add 5 times the second row to the first row to get a 0 above the leading one, just circled in green in the brown row. Okay, add 5 times the second row to the first row. And so then this red entry will become a 0. Okay, so the bottom row stays the same. The second row also stays the same. And the top row will change. So 5 times the second row, 5 times the second row to the first row, 5 times 1, 5 plus -5 is 0. This doesn't change the 3. This doesn't change the 0. But 5 times 1 is 5. 5 plus 2 is 7. So you get a 7 there. Okay, so now we have that this row is this. We have the brown row here. We have the green row. Okay, so we have that now. And so now we see that all the other entries, are now 0. Okay. So now we have this. So okay, the last matrix is in reduced row echelon form. Okay, so we now have matrix in reduced row echelon form because the fourth property is satisfied that for every leading one, all the other entries in the column is 0. And you see in the first column where there's another leading one, all the other entries are 0 also without us doing it. Okay, and so now we've succeeded at getting our original matrix to reduce row echelon form. So now let me just write a few things and then we're done. I have to quickly check to make sure if one student is here. Is Ahmed Hassan here? Ahmed Hassan? Ahmed Hassan, I see you right there. Can you turn on your mic to say here?
Yeah, here.
Okay, this is your first day here, right?
It's actually my second time. I was in last class.
Okay, I took attendance. Okay, so you're here though. I have you. Let me check you off here. Ahmed Hassan. Okay, stay there, Ahmed. Don't go anywhere. I'm gonna finish the lesson and then just stay on for a second while I check off the attendance. Okay. On the whiteboard. Okay, so so the procedure we have just described for reducing a matrix to reduced row echelon form is called Gauss-Jordan elimination. This algorithm consists of two parts: a forward phase in which zeros are introduced below the leading ones, and a backwards phase in which zeros are introduced above the leading ones. Okay, if only the forward phase is, I'm going to go to the next page now. If only the forward phase is used, and the procedure produces a row echelon form and is called Gaussian elimination. Okay, so applying the first 5 steps is called Gaussian elimination. If you apply all 6 steps, it's Gauss-Jordan elimination. Okay, and so, for example, in the preceding computations, a row echelon form was obtained at the end of step 5. Okay, good. So we finished that long example. Okay, so we're now done. Okay, so I'm going to save the whiteboard. So the whiteboard is saved as a PDF. Okay, I'm going to stop recording.